Hi, this is Roger from Kanka Labs, today with part 3 of our video series about AM magnetic antennas or resonant tank circuits used for radio reception. Now you might think, has this any importance except for AM or perhaps shortwave radio reception? Yes, it does. Because tank circuits where the Q factor is determining the performance are today found even in everyday life. Just think of these induction heaters here used in the kitchen. They also rely on the principle of a tank circuit, or think of wireless, no, not wireless, contactless charging with modern smartphones or other electronics devices. They also use the principle of two coupled resonant circuits, where the Q factor determines just the efficiency, how many losses you get when you carry your energy from the charger to your smartphone or whatever. And you might have seen, or I'm sure you know what this is, a Tesla coil. This also depends on the principle of two coupled resonant circuits. You perhaps can see here the primary coil and the more prominent secondary coil. And in Tesla coils also not only the coupling but also the Q factor of the primary and secondary tank circuits are quite important concerning the efficiency. And what else do we have? For example, NFC cards. They also have a little coil inside, and they also depend on the principle of resonant magnetic antennas, or in general resonant LC tank circuits. Now today we talk about the most important factor, especially when it comes to AM reception, and that is the Q factor. Simply because the Q factor determines three things in your radio reception. The first is a high Q factor amplifies the signal that goes into the coil. So if you have a Q factor of 100, the output of your tank circuit will be, the voltage will be 100 times higher than the voltage that comes through the electromagnetic waves into the coil. So that's quite a nice feature. Then we already talked about the bandwidth, that of course the Q factor determines how narrow your reception is. And we'll talk about every aspect, and usually optimizing Q factor means to get the highest Q factor as possible. But we will see it's not so easy even to get a Q factor of 100, not to speak of Q factors of 1000, because there are at least 5 things that you have to concern. We will see it's first of all the ohmic resistance of your reception coil, then comes the skin effect into play, then comes proximity effect. We have dielectric losses, we have magnetic losses like in loopstick or ferrite rod antennas, and finally even the wave resistance could come into play depending on the frequency and the size of your coil. So all in all, 5 or 6 factors have to be watched out for, and just getting a high quality, high Q factor AM reception coil is not an easy task. But we will talk about how to optimize all the factors that influence the Q factor. And in the next part I will show you an Excel sheet that I prepared, with which you can easily calculate and see how the effects interplay with each other, and you can construct, or at least calculate, your own coil and predetermine the Q factor and play around with the numbers so that you get the highest Q factor possible for your application. But that will be the content of the next part 4 in this video series. Perhaps I'll already give you the download link for the Excel sheet so that you can already play around a little bit. It's nearly self-explaining. But now let's start. We'll make some experiments, of course, again, and we'll do some simulations in LT-SPICE. And I think it's could become quite interesting because I myself have learned quite a lot about this topic in the last 6 or 12 months when we were designing a high-quality frame antenna here for commercial purpose for selling in our shop. So let's go to the workbench or to the lab bench and start with the first experiment. So let's first of all take a look again at how a lossy LC tank circuit looks like. We have our capacitor, usually a variable capacitor like this one here, which we first of all look upon as lossless, so as an ideal capacitor. The reason is because in 99% of all cases, the losses in the inductance, in the inductor here, designated as L, are much greater than in the capacitor. So we will concentrate on the losses in the inductor. And of course, what first comes into mind are the ohmic losses here, and we will measure that for one special reception coil just in a minute. To get you an imagination how the losses works, remember that the current and the voltage is circulating here between magnetic energy in the inductor and electric energy in the capacitor. And let's, for example, take a frequency of 1 megahertz. Then the current goes 1 million times per second through at least through the ohmic resistor here, because if we always have a resistance in an inductor, we can't get away with that except perhaps if we have a supraconducting coil, which is usually not available for amateur radio purposes. But here I already wrote R loss, so we will take this as the sum of all losses concentrated in series with the inductor. And you can compare this with the mechanical model of a spring pendulum. There we have the friction losses. The internal friction in the spring finally leads to that the oscillation just dampens out, and we have the same equivalent here in an LC tank circuit, where first of all the ohmic losses manage to dampen the oscillation, to dampen it out over time. And we of course already know the smaller the losses, the better the Q factor. That's immediately apparent. And so our task will be to find out which factors determine the total loss resistance and how to minimize them. So for a first experiment, let's just take this spiderweb or basket weave coil that you already saw 1 or 2 times in the other videos. It has 170 microhenries, as you can read, and has an ohmic resistance of 2.3 ohms. And now we will take these values into LT-SPICE and make a simulation and see if the ohmic losses are really responsible for the Q factor of this coil. And the Q factor of this coil is determined as somewhere around 100, at 1 megahertz frequency. So we will have to connect the reception coil with a variable capacitor, and we'll tune the capacitor so that the resonant frequency is exactly 1 megahertz, and that will be our simulation. And we expect a Q factor in simulation of something around 100, because that's what the real coil really has. And we'll see if the 2.3 ohms ohmic resistance are responsible for a Q factor of 100 with this special coil. So now here I've put our lossy RLC tank circuit. It's no longer an LC tank circuit, it's an RLC tank circuit. Into LT-Spice, you can see our coil with 170 microhenries inductance. We have our DC resistance of 2.3 ohms, and I've calculated the necessary capacitance for the variable capacitor to give a resonant frequency of exactly 1 megahertz. And this comes out to 149 picofarad. And now what we do is we'll simulate the first way how to determine Q factor. You might remember this from episode 2 of this video series, that we just make a frequency sweep. That's why we here have our sine wave frequency generator here set just to sine wave with 1 volts amplitude, and we connect it to the tank circuit and just measure the points or the bandwidth where the amplitude drops 3 dB from its peak value. And just to be 100% sure, you can see here we of course always have an output impedance of a frequency, of a real frequency generator, typically 50 ohms. By the way, in LT-Spice you don't have to put the units behind the values. It would be sufficient to write 149p or 2.3, just you can leave out the ohms, you can leave out the H for Henry. I've done this just for clarity, included the unit of the different elements. So now we make a frequency sweep, and just to be 100% sure, we make a logarithmic sweep, which is called decade sweep in LT-Spice, from 10 kilohertz to 100 megahertz, just to see if the resonant frequency is really at 1 megahertz. And what we expect is a very sharp resonant point centered at 1 megahertz, and steeply dropping off to lower and higher frequencies. Now let's do the simulation. We take the voltage here at the upper point of the tank circuit, and oops, what is that? This is a bell shape, okay, as we expect. It's also centered at 1 megahertz, but there is no sharp resonant point, so we must have done something wrong with our test circuit. And I've just put this in as a trap for young players, because just take a thought where the error is lying. The reason is we load our whole tank circuit just with the output impedance with 50 ohms, because here the voltage source behaves like a short, and so we have a direct connection from the upper point of the resonant tank circuit to the lower point via the output impedance of 50 ohms. And that's of course not how we can do it. We have to load our tank circuit as small as possible So that's why, if you remember, we measure this with usually with an as high resistance as possible. So we add usually a 1 mega ohm, or to be 100% sure, a 10 mega ohm resistor in series with the output impedance of the frequency generator. And now let's do the simulation again. Aha! That's how it should look. A very sharp peak centered at exactly 1 megahertz, and then steeply dropping off here in dBs. It's of course logarithmic, very sharply dropping off to the left and to the right. And now we can enlarge the center point just to measure the 3 dB points. We can do this either by drawing a box around the center, but the resolution is not high enough because I've only set 1000 points per decade. So we will change a little bit the frequency sweep. We don't have to any longer to take the sweep from 10 kilohertz to 100 megahertz. We just center it from 900, let's say 990 kilohertz to 1010 kilohertz. So we just only take a look at the 10 kilohertz to the left and 10 kilohertz to the right of the center frequency, of the resonant frequency, and we change to a linear sweep because we are now only looking at a very narrow frequency range. Do the simulation again. And here we beautifully see the bell-shaped curve of a tank circuit. And now we just have to find the bandwidth where the peak amplitude drops 3 dBs. Now, as you can always see in LTSpice here on the lower left, the dB values, the phase, and the frequency are displayed. And we have a peak amplitude of minus 26.5 dB. So if we go 3 dBs lower, that would be minus 29.5. That is around here. And now we go to the left and find a frequency of rounded 999 kilohertz, and to the right it's 1001 kilohertz. So we are, all in all, the 3 dB bandwidth is 2 kilohertz, 1 kilohertz to the left, 1 kilohertz to the right. And now the Q factor determined by this method is the center frequency divided by the minus 3 dB bandwidth, and that would be 1000 kilohertz divided by 2 kilohertz bandwidth, and that gives us a Q factor of approximately 500. And now we already know there must be something missing, because we know from real measurement that our coil in reality has only a Q factor of 100. So the DC resistance measured as 2.3 ohms of this coil cannot be all that comes into play. But anyway, if it would be all that is really determining the Q factor, then we would get a Q factor of 500. And you probably have already spotted these two formulas here. And that's how, if we know the values of capacitance, inductance, and the loss resistance, the series loss resistance, which is in series to the inductor, we already can calculate the Q factor. So we don't have to measure it, but it's always good to compare calculation and measurement. And now let's for example take the values we have here. We have to take the square root of L divided by C, so we get, or we put 170 microhenries divided by 149 picofarad take the square root and then finally divide it by the series resistance, which is in our case 2.3 ohms, and this gives us a Q factor calculated as 464, and that's just what we get here as estimated as rounded to 500 with the bandwidth measurement, or in this case simulated bandwidth measurement. So with this formula, if we know L and C, which is usually known, and if we know the total loss resistance in series to the inductor, then we simply can calculate the Q factor. And we will just in a minute make the second way, we will simulate the second way how to measure Q factor with a square wave. But first of all, let's explain what this here stands for. Now there's one very important concept. We can transfer this circuit with a series loss resistance into an equivalent circuit with a parallel loss resistance, and that's what the P stands for. The S stands for series loss resistance, and the P stands for parallel loss resistance. So, which means that in the equivalent parallel circuit, this resistor is placed here in parallel to the capacitor and to the inductor. So it's no longer in series. We will see how this looks in a schematic in LT-SPICE just in a minute. But first of all, let's calculate what the equivalent parallel resistance gives us. We have to first put the inductance L, which is 170 microhenry again, divided by the series loss resistance, now 2.3 ohms, and divide by the capacitance, 149 picofarad. And this gives us, if we round it up, we get 496K, 496 kilo ohms. So we will round this up to 500 kilo ohms. So let's remember what we get until now. We first of all see in reality the series resistance is responsible for the Q factor, but the DC resistance cannot be all that comes into play. There must be more, because we get a much too high Q factor if we only take the measured DC resistance than we have in reality. And second is, we can transfer this circuit into an equivalent circuit with a parallel loss resistance. And for the series resistance, we immediately know the lower it is, the higher the Q factor becomes. We already can see this in the formula, because the series resistance is in the denominator. If we lower RS, the series loss resistance, then Q becomes higher. And on the other side, in the parallel resistor must be as high as possible to get a high Q factor, because again, they parallel and series resistance behave in an inverse ratio, because here again the series resistor is in the denominator. So a low series loss resistance means a high parallel loss resistance. So perhaps take a minute to think about again about what we achieved until now, and then we will change to the equivalent circuit with a parallel loss resistance. So here we see the equivalent circuit with a parallel resistance. We've put in the same values, 149 picofarads, 170 microhenries, and as we just calculated, a parallel loss resistance of 500 kilo ohm. Now, to verify the concept, we just make again the same linear frequency sweep from 990 kilohertz to 1010 kilohertz, and let's take a look if we get the same result. And you see we got exactly the same curve, so obviously the concept is verified that we can replace the loss resistance here in series with the inductor with a parallel loss resistance of calculated as in the formula we just put in the calculator. And here again you can see basically the same formula as just before, but now with Rp on the right side, the parallel resistance, and not Rs, the series resistance. But now we make a second second simulations, and that is just the second method of determining Q factor. And that is, this time we use a pulse, a square wave pulse shape with 1 volt. The voltage doesn't matter here. And now we change from frequency sweep to transient analysis. So we take a look at how the circuit behaves if it gets excited with a square wave, and we just take a look at the first 500 microseconds, which, if we know that we have 1 megahertz resonant frequency, then there will be 500 cycles included if we look at the signal for 500 microseconds. So it will become clear just in a second. And you can see this, that it's here a little bit, how do you say, edgy. This is due to the limitations of LT Spice. This looks much cleaner, of course, in an oscilloscope, and the screen also doesn't resolve here the 500 oscillations. But what we can see is that the amplitude drops here exponentially. And the second way of measuring Q factor is we just count how many cycles we get until the amplitude drops to 1/2 of its initial value. So the initial value is here just by chance at 100 microvolts, and half of that is 50 microvolts. That would be here. And now we would have to count the number of cycles that are included in the time range from start until here, until this point. And if we would do this, we would count 100 cycles, and this number has to be multiplied by 5, and this gives the Q factor. And now 100 cycles times 5 gives 500, and so we get exactly the same Q factor by this measurement method. And anyway, now we have verified two things. First of all, we can look upon a lossy LC circuit, not only with a series loss resistance, but also with a parallel loss resistance. Second is the two main methods to measure Q factor give, of course, as in theory, the same result. We could either measure the bandwidth where the amplitude drops to 3 dB below its maximum value, and then we only have to divide the center frequency, the resonant frequency, by the frequency where the amplitude drops 3 dBs, or we take a square wave, we excite the resonant tank circuit, we measure the number of cycles where the amplitude drops to half of its initial value, multiply this by 5 and also have the Q factor. Or, of course, if we know the parallel loss resistance, we also can calculate it. Now you may ask yourself, well, what purpose does this have to transfer the circuit to this parallel resistance? I will give you the answer in a second when I show you the equivalent circuit of a tank circuit without the exciting frequency generator. Okay, now here I've again drawn the tank circuit with the parallel loss resistance, and now comes the important part. We know that a tank circuit that with a receiver coil for our electromagnetic radiation has also an output voltage, and so we can look at the lossy resonant tank circuit also as a voltage source, and as a voltage source with an internal impedance of exactly this parallel resistance. Or we could look at it as a current source with a parallel output impedance of the same value. Always these are, in our case, in our example, 500 k ohm. And this is of course important when it comes to radio reception, because we want to know, first of all, how large is the voltage that we have here, which is generated in the tank circuit by the electromagnetic waves. And what's still more important, what is the output impedance of our voltage source? And as you can see, with a very high Q factor AM reception coil, we also get a very high output impedance, and we have to take care of that, especially when it comes to crystal radios, because there are many things done wrong in crystal radios. And we have to remember this: the output impedance of our tank circuit is in the range of many dozens, if not many hundreds of kilo ohms, if we take care to get a high quality, high Q factor tank circuit. And now there remains the question, what is the reason why our real tank circuit, our real coil, why it does have apparently more losses than only the DC resistance. And therefore we will change to Wikipedia to take a look at the second way where losses come from, and that is the so-called skin effect.